For this session, we are going to do a small tutorial about how to use the software Mathematica to solve the exercises that were in the previous lectures. First, I would like to guide you through some basic Mathematica syntaxes for beginners. You can skip this part if you are already familiar with it. First, let's learn how to create comments. Comments are created with parentheses and star. So this would be a comment. And you type in regularly to produce input for the software. And when you don't use the stars and the parentheses, then there is not a comment. So if you type in like a number and then you evaluate that cell, the cell is this input right here that I am highlighting. You evaluate each individual cell by doing shift and enter. So the output is 3. You can use semicolon to suppress the output of the cell of the line. This is very similar to what we have in MATLAB. So if now I do 3 and then semicolon, then there is no output because the output is suppressed, as it is telling it here. In MATLAB, you had the ANS as the previous answer, but in Mathematica, it is used with the percentage symbol for the last answer. So if now I do just percentage and then evaluate the cell, then I have 3 because that was the previous answer. In Mathematica, all the variables are symbolic unless you assign a numeric value to the variable. So if I type in A, I don't need to declare the variable first. It will be already there. If I just evaluate that, it is A. So I can do like A squared 2. And then I will have the A squared as the output. And I can do A squared plus B squared. And when I evaluate, I get the A squared plus B squared. So there is no need for declaring that a variable exists. You can just use it right away. And same, you can do the assignment of the variable to a numeric value. So let's do B equals 3. And then if I run this, it will run in sequence. So the first output will be A. The second output will still be A squared plus B squared. But then when it executes the third line, it will assign 3, the number 3, to the variable B. So if I run this one time, I have this sequence. But if I run it again, now B has the value 3. So this line will execute to a different result. Let's execute this cell again. And now we have 9 plus A squared. You see that Mathematica organized the equation automatically, showing the number first and then the variables. Now we can create expressions. So Now we can create expressions. So let's create some expression as like A squared plus B squared, right? And you can see that Mathematica will change the color for B because it already had a value assigned, but not for A because A didn't have any value assigned into it. Now we create the expression and it will be again like 9 plus a squared, but this time it will be stored in the variable expression 1. So I can then plot expression 1 as a function of a. So I will plot it for a ranging from 0 to, let's say, 10, and then close the brackets. One important difference between MATLAB and Mathematica is that the functions are called with arguments within square brackets instead of parentheses. So you can see here that I am using square brackets for the function plot. And if I run this cell, again Shift Enter, I have my plot of the parabola 9 plus a square for a ranging from 0 to 10. One really cool feature from Mathematica is the use of substitutions for expressions in the symbolic expressions. So the substitutions are written down by the arrow operator. So you can say then expression 1. Let's see first expression 1. Expression 1 is 9 plus a squared. So let's say that I want to substitute a for another variable or a number. Let's do a number first. So the operation for substitution is the slash and then dot, and then you pass a list of substitutions. So let's do a to be substituted by the number 3, and then if I run the cell, I will get 18. If I substitute a for another variable, let's say c, then it will replace a for c, and so on. That aspect is very convenient, especially when we are doing modeling, because we can have the constants of the system. We can do constants of the system symbolical. So let's try commenting this thing. We keep the constants of the system symbolic and substitute at the end when we want to evaluate the model numerically. That way we minimize the use of numeric values at the beginning of developing the model and just leave it at the very end when we want to actually solve for a simulation of the model of the system. So one example would be creating a polynomial. Let's save that in a variable poly for polynomial, and let's do it with constants a1, right? So a polynomial of second degree, then a2 times x plus a3. So we have our constants a1, a2, and a3, and that expression is a3 plus a2x plus a1x squared. You see again how it organizes the polynomial. And we can create a substitution rule, but we save that in a variable. So we save this as constants for a variable. You can use any name. You can use any name for constants. I pick constant so that it's clear. Then we have a list of substitutions. So let's do a1 will be 1, a2 will be 2, and a3 will be 3. So you see that it stored this list inside constants. And now I can substitute poly1 to substitute into poly1 the list of constants. And you see that the output of the system is now with numerical values for the constants instead of A1, A2, or A3. However, those changes were not saved into the polynomial itself. So if we use poly1 again, it will be still as a function of x and the parameters a1, a2, and a3. So to save that, we can use poly1 equals and then assign that the result of the substitution. So that next time poly1 will be just the numerical formulation. We usually don't want to do that because the polynomial then will lose the flexibility of having the parameters. So let's rerun this cell so that I override the changes to poly1, and I will not do this anymore. So poly1 is still a function of the parameters. Now in the next line, I will create a plot of that polynomial by doing using the plot function of poly. Since poly is now a function, is still a function of x, then I will do poly of x, comma 0, let's do from 0 to 5. And if we run this one, it will not really work. So this line won't work, because the coefficients of the polynomial are still symbolic. So you see that there is no plot produced by this line. So what I need to do is to do the plot for poly1 with the substitution of the constants. And then I have my plot. So this is a very simple notation, because then I can have a cell where I can try different type of constants. So we can do constants, a set of constants 1 and a set of constants 2. Let's do a higher number here and a higher number here so that you can easily tell the difference. And then I can create two plots. Let's save this one under the variable p1 for the first plot, and under the variable p2 for another plot. And for the first plot, I will do constants 1, and for the second, I will do constants 2. And once I evaluate this, I will get two plots. If I want to compare these two, it will be more convenient to have them in the same plot. So I will suppress the outputs now, because I don't really need to show every single result of each line. And then when I run this, there is no output, but the result of the plot was recorded or saved in the variable p1, and same for the variable p2. Now I can use the function show. Let me move this comment first, and let's do show of a list of plots, and you can see that the two plots are there. I can also have the plots with some colors. You can assign the plot style, and we can do a color red for one, and we can keep the default blue for the other one. And then when you update, you can see the difference of the two polynomials. So let's go back. Let's double check this. So we have constants 1 that has lower values for the coefficients, and constants 2 that has higher values for the coefficients, right? So we can see that this first one, the one in red, is using constants 1, which is this one, making sense. And constants 2 is using this set of coefficients, which produces this result. I already have used lists, but lists are very important because that is also the way that we can create matrix expression. So if we want to create a matrix or a vector, we need to use lists. So I already use lists when I was assigning the coefficients. So this is a list. So a list is created with the curly brackets and a series of data, a set of data separated by commas. So I can do a list of numbers. I can save the list of numbers in a variable. Let's save that in the variable my list. And I can also do operations for lists. Let's suppress the output for this one first. Now let's do my list square. And we get the square of each one of the numbers in the list. But lists could also have variables or expressions or basically whatever you want inside. So let's do a variable c in here. And it evaluates the c squared for the second term of the output. So you don't need to have consistent type of data within the list. It can be anything. To access items in the list, you need to use the square bracket operator. You need to have that twice. So if you use just one, it will mean that my list is thinking of my list as a function. So if I do my list, the second item, and I try to do this, it's trying to evaluate my list as if it was a function. So it has my list and then the bracket, the square bracket too. So for accessing the item, you need to remember to use two sets of square brackets. And then we have the second item of list. And we can also do operations on it. And so on. So for a matrix or a vector is basically a list of items so that we construct the dimensions as the dimensions of the list. Let me explain this by showing you how to construct a matrix. So a matrix is a list with dimensions m times n, so m rows and n columns. Let's create a matrix size 3 by 3. So a matrix, I will store that in the variable a matrix. And then we have the first row 1, 2, 3. Then the second row 4, 5, 6. And the third row. And this is a matrix represented in Mathematica. One cool operator that Mathematica has is the double slash operator. So when you have some expression or some variable and then you add the operator at the end, it transforms the operator. So it is used as a notation for transforming some variable after you call the variable. So one operator that I want to show you right now is the matrix form operator. Will can show you the matrix in a nice shape. So if you just do this one, it is creating the matrix and saving that inside the a matrix variable. So matrix form is used to transform the output of matrix so that it will be displayed as a matrix, like more naturally. And it should be used only for display purposes. So you should remember not to save the output of a matrix as matrix form, but only have that to display the results. Let's now create a vector. So for a vector, I can do the same, but now with fewer dimensions. And let's show that in matrix form. And you can see that this is a column vector. And then we can do a product of a matrix and a vector. That will be a matrix dot a vector. And let's show that in matrix form as well. And there you go. So this was a set of functions and concepts of Mathematica that are important, and it's a basis for you to be able to implement the exercises from the lectures. So now that you know basic syntax of Mathematica, then we can do a second notebook for solving the exercises of the lecture for control theory. Let's start by creating a new notebook. Let's start with the first cell. Mathematica has also some extra libraries that you can think of, toolboxes from MATLAB that you can load before you are actually able to call certain functions, because they are not loaded by default. It's similar to toolboxes in the sense that they are optional to use and you can load them whenever you want. So let's load the library variational methods. That we will need to solve the Euler-Lagrange formulation, which is the method that I preferred for solving the inverted pendulum in a card. So we use the function needs, and we need variational methods. Now let's do the inverted pendulum using the Euler-Lagrange formulation. First, we need to define the velocities of each mass in the system. So we had the card, and the card will be m, will be mass 1. Let's call it mass 1 m. So the velocity of mass 1, let's call it v1, will be a function of x, which was the coordinate of the horizontal position. So v1 will be the derivative of x. The derivatives in Mathematica are created with the d operators, the d function. So the derivative of x of time with respect to time. And this is a column vector, which is why I am using the curly brackets. So we create v1, and let's visualize v1 in matrix form so that you can see. Oh, I forgot you need to have the context of the of the library, single quote like this, and now we don't have that error. Whenever you do something wrong in Mathematica, you will have errors that I probably should have covered in the previous notebook. You will have this report showing you the error of the expression, and then it will be very straightforward to find and correct for it. So here you can see that velocity 1 is x dot t for the x dimension and then 0 for the y dimension, because the card cannot move in the y-axis. Now let's do the same for the velocity of the pendulum. So pendulum, and to be consistent with the notation of our lecture, let's use M for the mass of the card, low uppercase, and then the pendulum will be mass 2, and we will use lowercase m. And we will define the velocity of that pendulum. Let's first define the relative velocity of the pendulum with respect to the card, which will be given by the angular velocity of the pendulum. So let's first create a tangential direction, a vector, unit vector with the direction of the tangent of the pendulum. Let's make use of the Mathematica math palette, which you can call from here as basic math assistant, or we can just type in using escape and then typing in the variables. So let's do theta for the angle, and theta is a function of t. So this will be the component in x for the tangential direction of the pendulum, and in y it will be negative sine of theta. So this is the unit vector, and then we are multiplying that one by the derivative of theta with respect to time, which is the angular velocity of the pendulum, and times L. So we can do L multiplied by the expression. So this will be the velocity of the pendulum of mass m with respect to the card, and we want the absolute velocity, so that will be v2. v2 will be the velocity of v1, which is the velocity of the card, plus the velocity relative of the pendulum with respect to the card, so v21. And let's suppress this one, and we have now stored in v2 the velocity of the mass lowercase m, and in v1 the velocity of the card, mass uppercase m. Let's do k 1 will be equal to, that will be the mass of the card divided by 2 times the norm of v1. So we can do it easily with the dot product. And we can do the same for the mass lowercase m, and then v2 here. So we have both kinetic energy. And then we can do the potential energy. And just to make it more clear, we can do both here. So T2 we know is 0, and T1 is m times g times L times cosine of theta function of t. So this is the potential energy of the pendulum, and the car doesn't really have potential energy because it is not moving in the vertical direction. So we can define this as T2 equals 0. Now we can compute the Lagrangian. And we know that the Lagrangian will be the difference between the total potential energy minus the total kinetic energy. And if we write this, if we execute the cell and we run this cell, we now have an expression for the Lagrangian, which is in terms of theta, x, and all the constants of the system, L, M, G, and everything we use for writing down the expressions of velocity and potential energy. So to continue, now we can get the actual value that is inside this. You see that this is a nested list, so it's a list inside a list. Let's just get the value of the Lagrangian as L and get the first item. Now we got this expression, and if we want to get the next nested term, we can do this, or we can also do this. So this will give us the expression, the scalar expression for the Lagrangian. And now we can use the function Euler equations, which was taken from the variational methods library. So if we use Euler equations and then we pass the Lagrangian, it also takes second argument, which will be the list of the generalized coordinates. You can always check the Mathematica help online to see all the arguments and more details of all the functions that we are using. So Euler equations of the Lagrangian, then the generalized coordinate will be theta, that's our first degree of freedom here, and x of t. And the third input, the third argument, is the independent variable, which in our case is time. So just calling this function will give us the model of the system. And I forgot the first set of square brackets. That's why this result is so strange. Let's add that one here and right there. So you see that it is a list of two equations. You can see that it is an equation because it has the equality term here, equals. So this one is the first equation, which will be the one obtained for the first generalized coordinate. And this one is the one obtained for the second generalized coordinate. If you see here, the notation is equals 0 instead of equals the generalized force. Because the Euler formulation from Mathematica assumes that there is no forces. So we can use some manipulation to transform the equations where the term in here is theta and the term in here is f. So let's do that one by first saving this in a variable called equations. That way we don't need to compute this again. And now we can do equations with forces. And we want to create a list of two equations similar to equations EQS. The first term will be evaluating the first term of the list. So this is a list right here. Sorry, the equations. Let me just go back and compute this so that you can still observe the equations, and then I can explain this better. So we have to evaluate the first term of the list, and we want to take the right side of the list. So let's do the list created by taking the first term of equations. So that this will evaluate to the left hand side of the equation. Run this one first so that you can see. This corresponds to the left side of the equation. And if we want to create an equation where this is equal tau, then we run that, and that's the equation. So let's do equations with force now using this expression right here as the first term of the list. And we can do the same for the second equation, which now will be equal to F, the force at the cart. Let's do F. But this will be with the second equation. So this one right here. We run this. Now we have the same system, but the right side of the equation is tau, and the right side of the equation here is F. Now we can simplify the model as we did in the lecture by just taking the first equation right here. So the equation that we care about, let's call this equation 1 equals equations with force, only the first in the list. And then we are substituting the acceleration, like we mentioned in the lecture, for the input of the system, which we called u of t. And we can also introduce some torque as a frictional term, which will be negative b times theta dot of t. You can create derivatives like this, or you can also use the d function. But this, I feel, that simplifies the notation. So I will use the prime or dot operator so that we can use a more compact way of writing. Now we have the equation stored in equation 1, and this will be our model of the system in the nonlinear representation. Let's then create a system. So Mathematica has an option to create a system as a nonlinear state space model, which is literally, that's the name of the function, nonlinear state space model. The first argument will be equation 1. The second argument will be a list of the states of the equation. So the first state is theta of time, and it's paired with the point of operation of the system that we said it was 0 for both theta and theta dot. Our second state is theta dot, and the point of operation is the 0 velocity for the 0 angular velocity for the pendulum. Then the third argument for the nonlinear state space model is u of t, which is the input of the system, and also a point of operation of u that we said it was 0 as well. And then the output of the system, we care about the theta in time. And then finally the independent variable of the system, which is the time. So this line creates a nonlinear system object that we will save under that variable. Let's suppress the output for this. Oh. And let's run this cell. And we will have the nonlinear state space representation. Here you see that the first row corresponds to x1 prime, and that's x1 prime equals x2 of t, and then this expression corresponds to x2 prime, and this shows the output of the system, which is x1 of t. So this automatically replaces our variables with variables x1 and x2, consistent with the representation that we were using in the lecture. So here you can compare these terms with the ones that we found for the lecture. Now we want to linearize the system, and in Mathematica it's very straightforward because we can use another function and then just pass that nonlinear model, because the nonlinear model was already aware of what was the point of operation of the system. So we can now use the state space model, which is linear, and we pass the nonlinear version of the system. And by just running this line, then you have the linear system. And you can see that it preserves all the symbolic notation of the parameters of the system, like G, L, M, and B. Now let's compute a transfer function for the linear system, obviously. I don't even need to write that for the linear system. We can compute the transfer function now. So let's do transfer function model, and we pass the linear system, and then we get a transfer function. It's as simple as that. Let's call this one P for plant, so that we keep the same notation that we were using on the lecture. So we have P equals this, and let's do also a controller. C of S. Let's call controller, let's call control, and because C is already a function for Mathematica, so I don't want to conflict with that. So I will call this one control, CTRL. And control for us will be just a proportional control to the error, which is just control equals K. Again, K here is symbolic, it doesn't have any numeric value. And let's compute the closed loop transfer function G as a transfer function model again of evaluating the expression that we saw for the closed loop control system, which will be C times a P divided by 1 plus CP. So let's do that evaluation here. Control times P of S divided by 1 plus control, plus control times P of S the second argument for a transfer function model, when we pass the expression, is what will be the independent variable, which is s in our case. And this shows us the transfer function of the system. Now we run this line and then we can see the transfer function. If you notice, there is a term here that can cancel out with this one, but the execution of this did not simplify that. We need to explicitly tell Mathematica to simplify things, so that we need to then include the simplify operator in the expression that we evaluated. And then we have the transfer function simplified right here. You can see that the transfer function is depending on the value of k and depending on the parameters of the system. Now let's create some constants for the parameters of the system, same as we did in our previous notebook. It's 9.8, then L1, M1, and B1. And we can create a root locus plot for the closed loop system, and then we replace the constants, and we are sweeping for k from 0, which is the open loop, to 12. And for the root locus plot, you need to give the parameter feedback type to none, because the expression g is already the closed loop system. A root locus plot with no without passing this parameter will have the negative feedback as default, and it is when you pass the open loop function in here. So let's do the plot of the root locus, and you can see that it marks with X the open loop poles, and it marks some point here showing the middle of the range of k, which goes from 0 to 12, so this is 6. So if you change this for 10, this will be displayed at 5. That's it. And if you want to have control of where you are placing these markers, you can pass another argument that is called poles 0 markers, and you just list the values. As a list. You can read about the different parameters looking at the help for the root locus plot. So let's do a marker at 5, a marker at 8, and a marker at 12, as we had in the lecture. And we need to sweep to 12 if we want to have a marker there, right there. So now you can see where the poles are located depending on the value of k, and we can see that with 12 it is stable, but with 8 it is not stable. Let's compute the response of the system for a value of k equals 8 and see how the system is actually unstable, and we can see how the response diverges as we found in the lecture. Let's have then the numeric transfer function. I will call this gn for n for numeric, then do g replace the constants for their values. And then we are also replacing now k for 8. So this line will produce a fully numeric transfer function that we can then use for creating a state response of the system. The state response arguments are a list with the numeric variable, then the initial state or the initial condition of the system. In our case, we were doing around 6 degrees, that's 0.1 radians, and 0 initial velocity for the pendulum. So this first is the transfer function and initial condition. Then we have the input for the system. Let's do no input, which means that we are not doing any acceleration on the card. And then the time range that we want to evaluate the state response. So we want to start from 0 and go to 10 seconds. And this gives us the state response. You see that the output is an interpolation function that is really impossible to visualize by looking at the output, because this is attempting to solve the problem numerically and give you the answer. We don't want to have the answer, but actually just plot the answer. So we can just create a plot out of this output by using the percentage symbol to call the answer. And the answer is as a function of t. You see that it is a function of time. So if we pass this and then the range of time, we have the response of the system, and it is plotting both x1 and x2, so theta and theta dot, as a function of time. You can just use one of the outputs. If I just want the position of the system, of the angle of the system, I can do evaluate of the previous answer and then find just the first output, which is x1 or theta, and then it will be just a single curve. We can use this cell now to play with different values of the controller gain. So let's do 12, and we can see how the system converges to 0, making the result of a stability. Let's try different values in between 12 and 8 and see what happens. And let's try 9. So with this short tutorial, now you know how to construct the nonlinear model in Mathematica, then compute easily a linear representation of the system, and formulate some controls using the root locus method. You can try practicing the different syntax that you learn with this tutorial, and try to run the examples for the full state feedback. In the description of the video, I will add a link for downloading the fully commented notebooks with the tutorial for Mathematica. That way you can run it if you have issues when you try to implement it by yourself. Thanks for your attention, and I hope you have fun playing with Mathematica to create models and try to tune the controllers of your project. Thanks for watching.